Let's begin step by step. So today we move on and we switch subject a bit, and we will talk about Pyretic, that is a language and a runtime system for programming software-defined networks. So how many of you know Pyretic already? No one?
Just
Thursday? Didn't you?
yes, just on the Thursday.
How was? What did you learn on Thursday?
Silence.
Basic stuff about Pyretic.
Okay, so today we will try to move on and learn some further, starting from the very basic stuff and also some of the somewhat more advanced features. Okay, let's start perhaps with the very basic. Today I'll try to do something new. For the first time I will use this system over here to draw things. So it will be a little bit experimental, but I hope, I believe it will work out. I have a nice notebook here with squares, so it will help me drawing. Okay. Okay, so let's see how this is gonna work out. First of all, how many of you remember what is a northbound API? A northbound, yes?
The connection between the switch and the programmer, the program, the application. While the southbound is the connection between the switch and the hardware.
You mean the operating system, not the switch. If you mean the switch, it's not correct. So, I mean, let's recall this very simple picture where we have a network operating system, and then we have some switches over here. So this is what is this that I'm drawing over here? Is it the southbound or the northbound API? Southbound, of course. Now, on top of the network operating system, in the high-level SDN architecture, we also have the vision for a northbound API. The northbound API is what sits between the network operating system and the applications. Okay, it's basically what we use to program a network. So this API. So far, until today, in the first two exercises, you saw the southbound API using POX. We had to write directly OpenFlow messages, packetings, flow modes, and so on. And essentially, you were programming a network using the southbound API. Okay, now Pyretic. I think what is one of the very first attempts to build a northbound API for SDN networks and OpenFlow networks. Okay. In particular, it is two things. First, it's a programming language. Which we can use to program a network. And unlike what we have seen so far in POX, it aims to provide a more high-level interface than POX. We can think of POX as an assembly for programming networks, while Pyretic is a first attempt to provide a more high-level interface that aims to make the programming of networks easier. And as you will see in the next exercise, the third exercise, the programs we will write are going to be shorter now compared to the equivalent programs that you wrote in the first two exercises for programming SDN networks. So they will be shorter, but it won't be necessarily easier for a beginner because you have to learn a bit the philosophy of Pyretic, and this might be the hard part. But once you learn it, it will be easier to write programs. Okay, and second, it's a runtime environment, which basically takes the specification we write, the Pyretic program we write, and converts that to low-level OpenFlow rules and packets. The nice thing about Pyretic is that we don't deal anymore with OpenFlow. We forget OpenFlow, we forget OpenFlow messages, and we deal with more high-level programming of a network. Okay.
From now on, we will use Pyretic instead of POX in our assignments.
It does use OpenFlow. And
Yes, but I mean, we will write in Pyretic or in POX.
So we will use it in the third exercise to learn, to see what a higher level language looks like. But then we won't need it. I mean, the fourth exercise is not going to be programming exercise, and the fifth is going to be something different. Now, briefly, the goals of Pyretic are to have a modular programming language where we define functions and we can reuse these functions also in the same network, in different devices, and possible in different networks. So we can have some, libraries of certain functions that implement standard procedures like a NAT, a firewall, and so on. And we can easily reuse these functions. Moreover, another key feature of Pyretic is that it supports composition. So this means, as we will see with examples today, that if we have one function and then a second function that implements a different functionality, like the first one could be a NAT, the second could be a Mac learner, and so on. Then if we want to implement a gateway that combines multiple different functions, which is common today, gateways do many different things. They don't do just switching or just routing. Then the goal of Pyretic is to make possible to easy compose functions. So for this reason it is called a compositional . Okay. And another key feature in the philosophy of Pyretic that we will try to understand today through various examples is that it encodes policies that dictate the operation of a network as functions. Okay, a policy is a function. Standard functions, as we know, and a function has an input and an output, of course. The input can be one or more packets, and the output is again one or more packets.
What do you mean by policy? For example, how would we use a function to implement what?
Okay. Sada, in the Pyretic terminology, a policy is generally any operation that the network does.
For example, a ping.
A ping is done usually by the end host, not by the network.
Okay, the network then.
Yeah, but an ICMP reply is done by the network.
Okay.
So this could be a policy and I clarify here that this is in the terminology of Pyretic. In the terminology of Pyretic, a policy is a definition of what the network is doing. Okay. Is this clear? Yeah. A little bit.
A little bit.
Okay. Okay, it will become more clear in the way. it's terminology. Okay. So let's move on and start right away with an example, and we will see the features of Pyretic as we go on. Okay. Okay, let's assume that we have this simple switch, and I'm going to use this in all the following examples. Okay, here is the internet, little nice cloud. So here we have a switch, and here we have two hosts. Let's say that we have packets coming in from here that are destined to this switch. The packets do not know that we have two hosts on the background. The load balancer wants to modify the destination IP of the packets so that half of the packets go to this host and the other half go to the other host. Okay, and I will write a very simple load balancer. The first part is a match statement. Okay, and let's say that we match half of the packets in a very crude way. We say that all the packets that have source IP starting with a bit of 1 and then we use this operator that says that subsequently that once we match these packets, then pass these packets to the following action. And the action we will do is that we will modify the destination IP of the packet to the IP of host 1. Okay, it's pretty simple.
Yes, but how would this split the packets into half? For example, maybe every source IP would be starting from one.
True, it might not be a very good load balancer,
Okay.
but it's just for the for the example. So then we use the plus operator, which is the parallel composition operator. Okay, and we say that in addition, so this is all the program that we need to do the load balancing. So here we have two functions, the function match and the function mod. Okay, these are functions. They are also called actions. So the function match takes as input one packet. If the packet matches the source IP, the specific predicate, we have it here, then it gives the packet to the output. Okay, it's pretty straightforward. Otherwise, if it doesn't match, it gives an empty output. Okay, pretty straightforward. And the function modify modifies a field in the header of a packet to the value that we give here. So in addition, we already saw the two most important operators of Pyretic. Pyretic has two composition operators, the parallel composition and the sequential composition. So this is the sequential composition and this is the parallel composition. Which operator? Parallel. So to be correct here, we need to define parentheses so that we are absolutely clear about it. Otherwise, I believe it's the sequential operator that has first priority and then the parallel.
The packet starting from 2 would be dropped, would not be handled.
This is a bit.
It's a bit, okay.
It's a bit,
okay.
in this example. Okay, so let's say that this is our load balancer. Okay, that is defined over here.
And what would it return? Case. It would modify something. It would return something to the LB variable.
So it will take a packet as input and it will give a packet as output. And so it will return a packet.
So LB is a packet now.
LB is a variable.
For error values, for example, if it returns -1, it would be error, or it would contain the packet, but with a changed field in the header.
No, it's not for error values. It's a function essentially. LB, it's a composition of functions. Okay, now let's write the code to do routing. Okay, and for routing, it's very simple. Packets with destination IP to H1, we should send them to interface forwarding out of port 1. Packets with destination IP to H2, we should forward them to port 2. And all the remaining packets, we forward them to port 3. Okay, so let's write this down. So here you see that we can compose predicates. We can use the OR here to say that we match the destination IP H1 or H2. And here we can have a negation. So essentially we say that when we don't match H1 or H2, then where do we forward? Done. Now, so here essentially we have an if-else statement. If this, then second condition, if that, else do that. If else. Okay. Now, Pyretic has also an alternative way to write these cases, so as we don't have to write long predicates as we have here. And for this we can use the if operator. It is written like you see here with an underscore. And let's write now the same thing with the if operator, and we will have two if statements nested, the one inside the other, to do the same thing here. So here we start a second if, a nested if. Let me consult my notes to make sure I'm writing this correctly. Okay. Is there anything missing?
Parenthesis to
A
close.
parenthesis.
I ask something because I'm a little bit confused. I understand that we use if to declare if something happened, do that. But with nested ifs, I can't see how the else going to be triggered, because I understand that the second, okay, we say if we have a match forward to port 1,
Mm-hmm.
then after the second comma declares an else statement.
Right.
Okay.
Does it declare that what Mihaly said, or is it the second argument of the third argument of the if statement? For example, I understood that we have if, the rule, if rule is applied, then go to port 1, or then, or if it doesn't apply, then go to the other argument. But the other argument is another if.
Right.
So what of those three is correct? I think those are two different things.
It's an else, basically. If I...
If
what is the difference?
The if takes always three arguments.
Three arguments.
The first is the condition, the second is the first
The
statement,
match action.
and the third is the else.
Right.
We could leave the third empty if we use it. If we want comma and then parentheses.
Yes, you cannot leave it empty, but you can use a special function that does nothing.
Okay.
So it has a special function that you could have if match forward. Otherwise, here you could have another action. If you want to leave it empty, you could have a special function that is called pass through.
Okay. I think the first way is much clearer, but I understand it better. And the second is okay.
Yes, so as Mihaly said, indeed, also for me, sometimes the first way is more clear what it does. But it's a little bit longer than the second way. And if you have more than two cases, these predicates can get pretty long. So when you program, you can use the one you prefer.
But if you have a lot of ifs, you will write lips in the end. You will have 10 parentheses in the end of the statement. If you find them.
True. Okay.
Ο πρώτος μου λέει σου.
Μπορεί να είναι και άλλοι.
Okay, so now let's see a third example. That is a monitor that we will have again in this switch. So now Pyretic provides three special functions that help you do monitoring tasks. These functions are the packets function, the count packets function, and the count bytes function.
Could we first define what is monitoring?
Give it a try. What?
Yes, I could understand that we can count packets, for example, in a specific network, but what do we monitor? The network, the traffic? What does monitoring do specifically?
So now I'm just talking generally what monitor is. Now specifically, it depends on the code we will write. So, for example, it could be a billing system that counts how many bytes have crossed through a link by a specific user.
So we define what we would monitor on.
Right.
Okay.
Right.
Is used by network administrators is something an incident.
Packets per second, for example.
If in a way,
Okay, great. Thanks. So Pyretic calls these three functions query policies. Query policies. Okay. And now let's have a look at how we can use one of them as an example to implement a monitoring task, which in particular will just tell us every second how many packets we have seen from a particular source IP. Okay. So we start first by defining a variable b.
Could you adjust it to the...
Great. So here the first argument of the function defines the interval. It's a time interval for this function. Count packets is identical with count buckets. With count bytes, count packets is identical with count bytes in the arguments. Packets is a little bit different in the arguments it takes. So here we say every 1 second. And next we register a callback that defines what we will do every 1 second. Okay. The count packets will just count the number of packets it has received. Okay. And every 1 second it will return this count. And here I will register a very simple callback that simply prints the count. So every 1 second we will print the number of packets we have received.
And if we do nothing, the The
Then-
result is lost.
Yes. Okay, and now there is one step missing, that is to give the input to the counter. Okay, and to give the input to the counter, we can use the match statement. And we say that we will match the packets that have source IP, let's say, X, and we will pass the packets that match to the counter. So B is a counter. It is also called a bucket in the terminology of Pyretic. It's a counting bucket. Okay, and this is our monitor. Okay. Okay. So let's say that here we assign this to the variable m. That
Could you adjust the paper a little bit?
okay, I'm sorry. That is the monitor, essentially, the implementation of the monitor. Here, let's say that we use route to encode this function. And here we have load balancing. So, one of the nice things of Pyretic is that it allows composition of functions we have. So, in this example, we could compose these three entities to implement a switch that does monitoring, that does load balancing, and that does routing, using the composition operators. So the composition in this case would be, first we will do the load balancing, in parallel we will do the monitoring, and finally we would do the routing. Okay. So, in this program shows one of the key features of Pyretic, that it tries to make the composition of different functions easier. Imagine now that we would want to do all these three functions together with OpenFlow. Then it would be much harder to design the OpenFlow tables, especially if we just had one OpenFlow table, that would do all these three functions. Okay, let's have a short break. Do you have a question? Yes.
How would we define the switch that these operations would happen on, would be applied? We have, for example, 10 switches. How would this specific line would go in a specific switch?
Good question. Okay, I will discuss this more in the second slot. So guys, shall we start? Are you ready for the second half?
Στα 10-12.
Yeah.
function counting packets when we assign the time. As a result, we have a packet that passed in this second. If we set time as 1 second, we have number of packets that passed in the last second.
Right. Right.
Okay.
Correct. I won't explain this today, but here, okay, note that count packets works the same as count bytes, but packets is a different function. Read the tutorial online, the documentation online, to see exactly how packets. What?
Documentation?
Yes, there is. No, I'm talking about Pyretic specifically. There is a little documentation online. If you search for Pyretic documentation, you will find it. Good. So we use these three functions to implement monitoring tasks. And these functions are called query policies. Okay, that's just a terminology. And we will see again these functions at the end because they are used to drive also the dynamic behavior if we want to implement tasks in which the behavior of the network changes over time dynamically. But for the moment, let's leave them out and let's proceed to the next task I want to cover today. And I want to follow up on the question I had at the end of the last hour that was specifically how do we know the switch in which a specific action is applied. In the examples I showed so far, I assumed that there was one switch and that the functions apply to that switch. If we have multiple switches, then we can use statements like this one. Okay. And then we specify what we want to do with the specific switch. Or we could match a switch and an import in that switch. So, in particular, what I want to point out that Pyretic has the following design feature. Each packet is a data structure. It's especially a dictionary in which the different fields, the source IP, the destination IP, the source MAC, destination MAC, are entries in the dictionary. So every field of a packet is an entry in this dictionary. In addition to the standard fields of a packet, in Pyretic, we say that packets are located. This means that the packet data structure has additional fields that specify the switch the import or the output of the switch. So this is the import or output of the switch, where a packet is located. Okay, for this reason, packets are called located packets. So when we write a statement like this one, this is applied to the switch field of the packet to decide if this packet is at switch 1 or switch 2 and so on. Okay.
So could we say, for example, match S1, import 1, output 2, and then the sequential, I think, the two arrows.
Yes.
LB plus M dot arrows route, for example.
Yes, you can say that. You can say that, you could say, but you have to write it like this. Match, switch, and match, import, it's deletion, and so on. And so on. So the packet model of Pyretic has first the standard header fields, one. Second, the location fields, the three fields I just mentioned. And in addition to that, we have some fields that they are called virtual location fields. Okay. The virtual location fields are used to implement another key feature of Pyretic that I haven't discussed today too much, and I will not discuss it too much. This feature of Pyretic is that it enables to specify virtual topologies on top of a standard topology. So, for example, we could have, a topology with many switches, and you could specify one big switch that is a virtual. So this is virtual and this is actual. Okay, that you can specify a virtual switch that describes your topology. The virtual switch specification is done using these virtual fields in the header of a packet.
Otherwise, it would be null.
These fields will be null, yes. Okay. So far, we have seen the match, the mode, the forward actions. So we also have the drop action, the flood action, the pop action, the push action, and the pass through or ID action. So who can guess what pop is doing? And we also have the move. Okay, actually pop is very difficult and I think no one will guess it. So let
Can I give it a try?
if you guess it, I mean,
One.
if you pass.
Let's say we have a queue in the network, and we use a stack to push the packets. And when it is time for the packet to travel, then we pop it, and otherwise we push it into the queue.
Nice. Actually, you got some terms right, but it's wrong. Sorry.
It's about flow modes.
What?
Pop, it's about flow modes.
No. Actually, Pyretic has the feature that when we have a header field, let's say the source IP address, we can, this is not actually a value, it's a stack of values. And this is used when we build virtual topologies, so as we assign another set of values to the fields that are that have a meaning only in the virtual topology, but not in the actual topology. So this is why both the pop and the push and the move function are used for operations on this stack of values. But this is one of the more advanced features of Pyretic that it's a little bit, we want to use it to match but we'll use it a little bit. Okay, flood and drop, you know them, all right? Okay, so let's do now a PI. We have a little PI. Can you distribute them?
It's between 3 or
2
2.
or 3 as PI.
Hello.
Εσύ με αυτόν τον
Okay.
τρόπο, με την πρώτη.
So, who says B? Who says C?
Εγώ θα λέω B.
D? A? Okay. So, in this example, we see the other function I mentioned, the function package, that is our query policy, that has 2 arguments. The correct answer is B. Okay. The first argument specifies that it will return only for the first packet that it will receive. If this was 2 or 3 or another number, it will return for the first 3 or for the first 4 packets that it will see. The second argument specifies if we want to group packets by a specific combination of fields. Here we will group them by source IP and destination IP.
Νομίζω ότι...
So in other words, in simple words, this function will return for the first packet of its unique source destination IP combination. And then we can do something with this. In this case, we will just print it. But now I will use this to move to a more advanced feature of Pyretic that will be the most advanced thing we will see today. That is the composition of dynamic policies. Policies that will change over time. So far, in the examples we saw with the load balancing and so on, the operation of the network was static. Okay. In the code we wrote. Okay, so let's step by step move to a more advanced feature of Pyretic, that is the composition of dynamic policies. So, and we will see how, with an example, how we can implement a learning switch. Okay, a switch that over time learns the MAC addresses that are associated with the ports of the switch. So we defined a class, yes? Hey. Invisible. Okay, we defined the class learn. Okay, and then we defined the init function. Okay, what is this?
We take the first packet of the combination source MAC and switch.
Correct.
We learn every source MAC of the switch.
Of every switch.
Of every switch.
So when we have dynamic policies, we will register a callback that will update the definition of the policy that we have for the specific class. So here I will add a function update that we will define later on. Okay, so you see here that a query policy is used to drive the dynamic learning of the MAC addresses. Okay, so we have a query here. And here a function that updates the policy of the learning switch. Okay. So in Pyretic, a dynamic class, a dynamic object like the MAC learner here has a special variable that is called self-policy. This variable defines what this object will do when it is instantiated. So remember, now we are in the init procedure, and here we will define the initial behavior. Okay? So the initial behavior of the MAC learner will be to flood. Okay, it floods all the packets, and in parallel, it sends every packet received to the monitor here. Okay, so when this class is instantiated, in the beginning it will flood all packets, but when a packet is flooded, is also sent to the monitor. And when we go to the monitor here, as we said before, the first packet for each unique switch and source MAC will trigger an update. Will trigger the update. So now let's define the function update to see what it will do. Okay, are you with me until now? Yes. Okay. Because now you will lose me. So it's a little bit more complex, the first step. Yes.
Why update is out of scope of the class?
Let me see.
It's out.
No, it is not actually. That's my mistake. Yes, it's in scope.
Because it takes out.
Yes, thanks. Okay, let's assume that it's in scope. So, as I said before, the update will update the policy, the variable policy that defines what the Mac learner is doing. So, the following might confuse you, but I will try to explain it. Okay, so here we have a match statement that matches the destination MAC and the switch. And here we close the match statement. So the new policy will first match for the destination MAC and the switch. The destination MAC will take the value of the source MAC that we just learned. Correct? This is what a learning switch does. You learn by looking at the source MACs, but you use the switch table to forward based on the destination MAC afterwards. If this is matched, then we will do forwarding. To the import where we saw the source MAC. Okay. Otherwise, what do we do? Who can find it?
I would say drop. Since we
It's not correct. Add plus. Yes, it's flood plus B, it's correct. But it's not exactly correct. Self.policy? Self.policy, correct. Otherwise, self.policy. So this variable, over time, for every new packet, gets extended with more and more match statements that match the MAC addresses of the packet. So in the first time it will be flood, but otherwise it will be it will be extended. Okay, here this close, and here we close the statement.
We take it again.
Yes, yes. From where, Sava? From the beginning.
From maths. Yes.
From the maths? Yeah. Okay. Okay, I will do that. Do you want perhaps to ask anything else before I restart? Okay. So here we have a match statement that says if the destination MAC is equal to this value and the switch is equal to this value.
The first value is source MAC.
Yes.
Okay.
So we learned the source MAC. That's why it's a source MAC. Then we forward to this value. That is the import of the packet. The port at the port of the switch, essentially. Otherwise, we stay with the self-policy. Something that might help you here is to write the if statement in the expanded form. Okay, so if we write this in the expanded form, what would it be? Match n is the value then forward, and here again we have a value. Otherwise, and here we have if not match, and this is the same. Okay, I'm not repeating it, it's the same, it's just the not. To the self-policy. That was before. So at the very first time, this will be flood plus B. Okay. Do we have, can I have the PC to show something?
Yes, just press the button from the
Oh, that's so cool, huh? Okay. So here you can see the documentation of Pyretic, and here is we have the dynamic policies. Here you can read also another example with a dynamic policy. This is a round robin policy that does round robin load balancing. You know what is round robin? No? It means that if I have 3 servers and I have packets coming in, the first packet goes the first server, second, third, first. So you do it in a round fashion. Make sense?
Yes.
Okay. So this is also dynamic policy. In this implementation. Here you can read more. Another example of a dynamic policy. Yes.
Could we take an example for, let's say we have a packet in our network with source MAC 1 and it goes through the switch 1. How would this packet go inside update? For example, what would it match and what would it do?
Yes. So the very first time we would see this packet, we would flood it. So the self-dot policy, let's assume that this is the very first packet in the network. Okay. So we said that the self-dot policy defines how the learner works. Correct?
Okay.
So the very first time this would apply, so it would be flooded. And here we have the parallel composition. So in parallel, it would also be sent to B. Okay. So if we go to B, B is a monitoring variable. And here, this variable will return the first time it would see a packet with a unique source MAC and switch combination. Okay, so this is the very first packet we see. So of course it has a source MAC that we haven't seen again. Okay. So bucket will then trigger the callback. It will trigger the update only for the first packet, not for the remaining packets.
One moment. What would the flood do then?
The flood would flood the packet in all ports. But this would happen in parallel. So B and flood take place in parallel.
So it would flood the packet in every source MAC, but we would just collect the source MAC and the switch combination, the packet that refers to that.
Sava, it would flood the packet to every port.
Of the switch, okay.
To every port. Okay.
And in parallel, what would B do?
It will send it to B, that is the monitoring bucket. Okay. Now we are at the very first step, and B, because it hasn't seen this source MAC before, it will call back update. Okay. And then we would go to update, and update would rewrite this variable. It would rewrite this, and it will say, before you were flooding, but now you will not be flooding anymore. You will first check if this match statement holds, and if this match statement holds, you will do forwarding. If this match statement doesn't hold, you will do flooding. Okay. And this will happen for every subsequent packet that is unique in source MAC.
So the third argument of if, the self-policy, refers to the self-policy of the constructor.
Yes, it's recursive. It's recursive. So the second time it will happen, the self-policy will have this value now. So we will rewrite the self-policy and it will have this value. Now the next packet we have, we will rewrite this value and this will give us a new value for the self-policy. It's recursive. Okay, so one last thing. If you want to, so I have also slides online. You can read the slides if you want to learn more. And also, 2 years ago, we recorded some lectures from this course, and we had this lecture back then. And if you go to Open Courses, University of Crete, and if you go here, you have to log in. So there is a lecture that is recorded about Pyretic. It's a good lecture that has additional material. They only give it's unfortunately in Greek because back then we were doing the course in Greek. So let me see which lecture it is. So it's this one. Oh, there you go.
Γνωρίζουμε στο OpenFlow έχουμε και μια σειρά από καταχωρητές που μετράνε τον αριθμό των bytes και των πακέτων που έχουμε δει.
Okay, the lecture is 1 hour. It doesn't cover the dynamic policy because there was some problems with the recording back then. But it covers the first part, but it's a good lecture. That's why I advise you to watch it if you want to learn more.
Thank you.
Okay, so thanks.